business. No, great. Let's get down to it then. So we're talking about inverse functions, and the thing that I mentioned at the very end last time was not all functions have an inverse, and in order to have an inverse, the function needs to be what we call one-to-one. So maybe I'll just refresh our memory about why it needs to be one-to-one. Remember, the whole point of the inverse is f of x equal y means that f inverse of y equals x. So the inverse is supposed to kind of do the function backwards, or it undoes the function, something like that. But if, for example, f of 2 equals, well, maybe I'll say, so, sorry, on my scribbler I can just erase and replace. I'm not used to this. I have to actually scribble it out. If f of 2 equals 3, then f inverse of 3 equals 2, right? That's the point of the inverse. It does the opposite, okay? There is a problem, though. If f of, let's say, f of 1 equals 5, and also f of 3 equals 5, this is not a problem for f. Like, it is possible to have a function, f of x, which obeys this formula, which acts this way. But this is a problem concerning the inverse. So then I would just say, what is f inverse of 5? It seems like it would have to be both 1 and also 3, and that's not allowed for a function. A function is only supposed to have a single value, right? So this is a problem. It can't be both 1 and 3. So here, f inverse is not a function. And we want to avoid this scenario. When I talk about the inverse of a function, I want it to be also a function. So certain functions have inverse functions, certain other ones do not. And the problem, the thing which can make you perhaps not have an inverse is when something like this happens, where you get the same answer for two different x values. If that ever happens, then there's not going to be an inverse function. And the word for a function which never has the same values is called one-to-one. So I'll write this as a definition. I think I said this last time, but I'm going to write it a little bit more formally this time. So I'm going to say f of x, a function, is one-to-one if sort of informally, I'm going to say something like if no y values are ever repeated. Like the y values are always different for different x values. That's actually how I'm going to write it. So here is what I'm going to say. F of x1 is not equal to f of x2 whenever x1 is not equal to x2. All right? This is a little more technical than what I said last time. But your interpretation of this, how you should read this, is just the y values are different. Whenever the x values are different. Right? Of course, if I just use the same x value twice, I'm going to get the same y value. But what one-to-one means is that you always get different y values when you use different x values. All right? So this is the definition of one-to-one. Any thoughts about that? So an example of a function which is not one-to-one, for example, f of x equal x squared. It's not one-to-one. That's because it's possible to have f of something equals f of some other something. Since, how about this? Can we fill in the blanks here? Can you give me two numbers where you get the same answer if you square them, even though they are two different numbers?
Say 1 and negative 1?
Yeah, how about 1 and negative 1? This is exactly what I thought he was going to say.
Great minds think alike, Professor.
Yeah, that's right. F of x equal x squared is not one-to-one because, in this example, of course, this is 1 squared, which is 1, and this is minus 1 squared, which is also 1, right? So in this example, f of 1 equals f of minus 1. Okay, I will say even though This kind of goes without saying, but I might as well say it because it was part of the definition, even though 1 is not equal to -1, right? So these are two different x values, but they have the same y value, and that means it is not 1 to 1, all right? So it's not 1 to 1. All right, sometimes people write this 1 to 1 like that. It's sort of a shorthand, 1 to 1. Makes me a little nervous. It looks like 1 minus 1, which equals 0, which is not what I mean. All right, that function is not 1 to 1. Great. This is something actually that you can see fairly clearly on a graph. What happened? My iPad timed out because I'm not touching it enough. It needs touch. All right, I hope the focus is still good. Okay, it is not. Sorry about this. All right, I think I'm good now. I'm learning as we go. Okay, we can see this on a graph. That's what I was saying. I mean, we can see whether something is 1 to 1 or not by looking at a graph. So, for example, here is a function which is 1 to 1. This one is 1 to 1. The matter of are there any y values which repeat, you can see very clearly by sort of sketching in, or I mean, you don't even have to draw this. You can just imagine it if you know what to look for. Imagine some horizontal lines drawn on the graph. These horizontal lines will indicate specific y values, right? And you can see on the graph that these specific y values here, they only occur once on the function, right? There are no y values which occur twice on the same function. And so this one is 1 to 1, whereas a function like this, for example, this is not 1 to 1. And I can tell because there are certain y values which are repeated on the graph. These ones down here are not. You only get one of them. But for instance, up here, there is a y value which occurs 3 times on this graph. All right, and that's why it is not 1 to 1. So it's these guys here, which I sort of focus on and identify. This function is not 1 to 1 because of those guys there. All right. There's actually a name for this way of looking at the graph and telling something is 1 to 1. Anybody seen this before?
Yeah, we can do like the horizontal line test. Right?
Yeah, this is what they call the horizontal line test. You might have heard that on the playground, on the streets. The horizontal line test. You look at the function and you just imagine any kind of horizontal line. It should only hit the function one time. If that's true, then it is 1 to 1. And if the line hits the function more than once, then it's not 1 to 1. So let me just write that again. Come on. Here's the top of the paper. There it is. All right, so f is 1 to 1 if it satisfies the horizontal line test is what we call this. And that just means that any horizontal line on the graph will impact the curve I will say no more than once. It's okay if there's some y values that are just completely absent. That still counts as being 1 to 1. So if you draw a horizontal line and it just doesn't touch the curve at all, that still is okay. But what's not okay is if the horizontal line hits the curve twice, or any number more than once. All right. So common functions that we know and love: y equals x cubed. Is that 1 to 1 or not? Well, I hope you know the graph of x cubed looks like this. What would you say? Does that look like it is 1 to 1 or not 1 to 1? You can give me the thumbs if you want. Is not? What do you say? I see some thumbs up. It is 1 to 1. Because any horizontal line you can imagine will hit this curve exactly one time, which is, that's what the horizontal line test is all about. Okay, or an example of one which is not one-to-one, how about another favorite function? How about sine of x? This is definitely not one-to-one, because if you imagine a horizontal line, it will hit the curve many times, right? Or 0 times, although 0 times is okay, but many times is not okay. So this is not one-to-one. All right. This is generally easier than if I just gave you an equation of a function. It's not so easy to tell just by looking at the equation if it's one-to-one or not. If you know what the graph looks like, then it's easy to tell. You can just look for the horizontal lines. All right. Any thoughts about this? I think this is probably familiar to you from high school. All right, great. Remember, the whole point of this was about inverse functions. So let's try and I want to tie this maybe a little bit more specifically to inverse functions. So if f is one-to-one, then that means f inverse is a function, and the definition of f inverse is f inverse of y. This I wrote a few minutes ago. I'll use a slightly fancy phrase here. F inverse of y equals x if and only if f of x equal y. All right. This phrase, if and only if, I think you've probably heard that in other math classes. It means these two things which I'm saying on either side here are logically equivalent. That is to say, if the one is true, then the other is true, and also if the other is true, then the first one is true. They mean the same thing. So if you want to know what does f inverse actually mean, this is what it means. F inverse of y equals x means that f of x equals y. All right. This suffices to make a definition of what the inverse function is, although you will see it's not so easy to use this description of the inverse in practice, but we'll get to that a little bit. I want to try to draw a little weird diagram here. I don't know if you talked about this point of view in your youth in high school, but how about domains and ranges as it pertains to inverse functions? I would like to think of sort of the domain. Remember, the domain is all the possible, the set of possible things you are allowed to plug into the function. And then the range is all the answers that you get out of the function. So you could sort of imagine it as if like the domain is some kind of blob of stuff, and the function takes those things and kind of turns them into another blob of stuff. I'm kind of thinking of this more in terms of set theory or sets of numbers. The domain is a set of numbers, right? Which you typically would think of as like, it's usually like an interval in the real numbers or something like that. But whatever it is, it's just a bunch of numbers which make up the domain. And you can think of f as some kind of transformation, which it takes those numbers in the domain and it turns them into some other numbers, and that makes up the range. What does the inverse do? The whole point of the inverse is it goes the other way around. So the inverse is supposed to sort of fill in that way in the same picture, right? The inverse should take the things from the range and turn them back into things from the domain, right? That's the whole point of the inverse. And so we can say actually what the domain of the inverse is and the range of the inverse. I don't know if this is confusing. It's not so confusing. So the domain of f inverse is, anyone want to complete the sentence here based on what you already see on the paper there?
F. Would it be like the domain of f negative 1 is f?
Maybe I know what you mean, but I mean f is another function. You should be The domain of F inverse is some set.
Oh, it's the range of F.
It's
I'm
the
sorry.
range of F. Yeah, that's what I...
My bad, I was going at that from the wrong side.
The domain of F inverse is the range of F, right? All the answers you get out of F, those are the things that you're supposed to plug into F inverse, and then you get the what you started with again. And similarly, the domain of F inverse is the range of F, and the range of F inverse is the domain of F. It's all just doing the opposite thing, right? Going the other direction. That's what the inverse is. Excellent. Another way, or a more specific way to say this, and this is also something that I said last time, F inverse of f of x is x again, and f of f inverse of x is x again, right? F inverse, oh, my camera just went out again. Did it? No. It didn't, but I can't see it anymore. All right. Your technological ways are strange to me. Okay, yes, F and F inverse, they kind of cancel each other out. So this is a more sort of algebraic description of what I was just saying. That if you actually plug in f of x into f inverse of x, what you end up with is just x again. All right. Another way of saying the basic idea is that f inverse and f are supposed to cancel each other out or do the opposite of each other or something like that. All right. I think everybody gets it, I hope. Let's talk about, if I give you an equation, can you actually find the inverse? I'm confusing myself with the papers. I have my notes written on a piece of paper, and what I'm doing is just writing them again on another piece of paper. This feels strange to me. And I end up with two pieces of paper with the same thing written on them. I'll put them up on the refrigerator. Okay, how do you can find the inverse of a function using the equations. So to find the inverse, I will say sometimes you can find the inverse of a function sort of algebraically using equations, and this is probably something that you learned how to do in high school. Here's a simple example. Find f inverse for f of x equals x cubed plus 2. All right. There's a few different ways that people learn to write this down. As usual, I'm going to do it, I'll do it how I do it. If you learn some other way to do it, that's fine with me. You can do it however you like, whatever works for you. What you do is you start with this. You write y equals x cubed plus 2, and then you solve this for x. All right, so in this example, I would solve for x by, first of all, subtracting the 2. It says y minus 2 equals x cubed, and then I take the cube root to solve for x. X equal cube root y minus 2, right? This is basically the answer. This is what the inverse function is. I will write it as a function like this. F inverse of y equals cube root y minus 2, right? The thing I have solved for x, which means I'm writing the whole function depending on y. And then just because, like, from here, this is the inverse function, although some people don't like writing a function with the variable called y. They would rather always have the variable called x. So I will just say, or if you want to, you can write it this way. F inverse of x equals cube root x minus 2. Of course, we all know it doesn't matter what you call the variable. You can call the variable whatever you want. You're still talking about the same function. So when I write f inverse of y is cube root y minus 2, that's the same function as f inverse of x equals cube root x minus 2. Just people like using x instead of y a little bit better. All right. Excellent. I would like to say, though, this, like I said, this is probably something that you learn how to do. Some people learn, when I was in high school, I think my teacher taught me, you should begin by interchanging x and y and then solving for y again. You can do that if you want to. That seems a little weird to me now as an adult. Looking back at my childhood, it seems strange to me. Oh, I want to say this procedure here doesn't always work. This was kind of a simple example. You have to take the cube root, but it's not so bad. I will just say this won't always work. For example, here's one where it doesn't work out so nicely. What about this function, y equals x cubed minus x plus 2? Almost the same function, but I inserted that minus x, right? The previous example is just x cubed plus 2. I stuck the minus x in there. How bad is that going to be? In fact, it's going to be quite bad, actually. That minus x really screws the whole thing, and this becomes impossible to do. What do you want to do? You want to solve for x here, right? That's the procedure. Solve for x. Well, I could subtract the 2, I guess. Y minus 2 equals x cubed minus x. Now what are you going to do? Anybody know how to solve for x right there? The answer is not really. It's not really possible to get x by itself. If I were desperate, I might try to factor here. I get x times x squared minus 1, which in fact I could factor even more if I wanted to. X plus 1, x minus 1, right? But still, this is kind of making it worse. Now I got 3 x's on the page when I used to only have 2. Your goal, remember, is to solve for x, and right here you just can't really. Can't solve for x. Now, does that mean there is no inverse? No, not necessarily. It just means you don't know how to solve for x in an equation like this. All right. The moral of the story is solving for x is not always possible to do using algebra. Even if there really is an inverse, it's not always something that you'll be able to figure out just by you know, changing the variables around and solving for x again. All right. Okay, one last interpretation of finding the inverse is on a graph. Again, I'll say, what about the graph of f inverse? What about the graph, and how, if at all, does the graph of the inverse relate to the graph of the original function? What happened? I lost my... something happened. Can you still hear me? Yes?
Yeah.
Okay, it's back now. You know what I did? I did nothing. It went away, and then it came back. Is it really back? Okay, it's back. All right. Sorry about that. Sometimes they just stop working, and they start working again. Okay, what about the graph of the inverse? Remember, the process for finding the inverse involves starting with something in terms of x, a function written in terms of x, and then changing it around to be the same function but written in terms of y instead of x, right? That's why you solve for x instead of y, okay? So the whole idea of finding the inverse from that point of view is f inverse comes from exchanging the roles of x and y. Right? You write the function which used to be written in terms of x. You instead decide to write the same function but in terms of y. All right? F inverse comes from exchanging the roles of x and y, and that means you can actually, there's a cute trick for doing this just by looking at the graph of something. For example, if I had the function, let's say f of x is this line, the line of slope 1/2. How could I write kind of the same graph, but just interchanging the roles of x and y? Well, this one goes over to x equals 2 and up to y equals 1. F inverse would be this sort of this way around, right? The same idea, but everything that used to be a x is now a y. So it goes up to y equals 2 and over to x equal 1. All right, this is the inverse, f inverse of x. And if you think about there's a cute way to think about doing this. How do you go from this picture here to this picture here? It is you just interchange the x-axis with the y-axis. You kind of do a little flip it over somehow. Imagine that you are swapping the x-axis with the y-axis. What that means, another way to say that, a little clearer maybe, is we are, reflecting the x-axis into the y-axis, and vice versa. So what it looks like is, you can imagine doing this on just one picture. Same function I started with. What does it look like if you were to interchange the x and the y-axis? It looks sort of like you were doing a mirror image around this 45-degree diagonal line. So this is f of x, this is f inverse of x. All right. To get the inverse, you do this kind of diagonal mirror image. And the result is a graph of the inverse. So for example, in a more recognizable function, if I begin with this is x cubed, the inverse of x cubed, of course, is the cube root of x. And you can see the graph of the cube root by doing a reflection across this line. And it looks sort of like this. I would have done these in two different colors. But this is the graph of cube root of x. And that really is what the graph of the cube root looks like. You know, if you want to, you can graph it on your calculator. That's really what it looks like. All right. So this is the graphical way to see what the graph of the inverse is going to look like. All right. This also, I think you probably did in high school. And as usual, if they talked about it slightly differently, that's fine with me. All right. Now I'm going to say some stuff about the inverse which probably you didn't do in high school. I don't know, maybe, but I know I didn't. I wasn't any kind of like math wizard when I was in high school. I sort of didn't realize I was good at math until I got to college, because I'm not so good at multiplying numbers in my head and that kind of thing. And so when I was a kid, my teachers never thought I was that good at math. But real mathematicians don't spend all day long multiplying numbers in their head. It's true. It's not actually a skill that makes you a good mathematician. It just makes you a good accountant or something like that. No shade on accountants. Okay, how about continuity and derivatives as it relates to the inverse? Continuity and derivatives of inverses. Let's talk about continuity. What I want to say is something, actually I'm just going to straight up say it and I will explain to you why it's true. I'm going to write this like a theorem. A theorem is the fancy mathematical word just for like a true fact, which you can prove. We are going to, in this class, you know, we're going to do some proofs in detail and some I'm just going to try and explain the general idea of the proof. Here, this is an example where I'm going to explain the general idea, although the real proof is not much more complicated than what I'm going to say. The theorem is if f of x is continuous and one-to-one, then f inverse of x is also continuous. All right? So basically, if the function is continuous, then the inverse will also be continuous. I had to say and one-to-one just because if it's not one-to-one, then there is no inverse. So it needs to also be one-to-one in order for this theorem to make sense. But it basically says if the function is continuous, then the inverse is continuous. Why should you believe that? Well, it's because of this business that I just said about the graphs, right? Remember, continuous means, from some informal point of view, it means that there are no holes in the graph, or there's no break in the graph of the function when you look at it. It's all in one nice, smooth piece, right? And if you believe me when I said to get the inverse, you do this reflection thing, then the inverse is also going to be in one nice smooth piece. So if f is continuous, then the graph has no holes in it. This is my sort of informal version of a proof of this. This is why you should believe me. If f is continuous, then the graph has no holes in it. So the graph of f inverse also has no holes in it. That's because the graph of f inverse is obtained by reflecting the original graph of f, right? And so if there's no holes where what you're starting with, and you do this reflection thing, there's still going to be no holes in it, all right? That's the idea. So the graph of f inverse has no holes, so f inverse is continuous. Right? This is my informal explanation of why that theorem is true. Because the graphs play nice when you do the reflection thing. Okay? What about derivatives? Now, derivatives, there's a similar kind of theorem that says if a function is differentiable, then the inverse is also differentiable. Although there are some caveats. So I'm going to say, what about derivatives? What I would like to say is if f is differentiable, that means the derivative exists, then f inverse, not prime, f inverse is differentiable. Is that really true? This is, I'm going to say, this is almost true. That's why I put it in quotes. It's not quite true as I wrote it right there. Almost true. The issue is that sometimes when you do this reflection thing, you can mess up the slope or cause something which has a good slope to turn into something which has a bad slope. And here's an example of that. How about my favorite one-to-one polynomial, x cubed? It does this, right? And anybody happen to know right there what is the derivative? The value of the derivative right there, the slope of the tangent line? Or you could just do the derivative of the formula. When I use x equals 0, what's the derivative going to be right there? I'm trying to write, what is f prime of 0? Can anybody shout it out? Do you remember how to do the derivative? We haven't done the derivative in a little while, I know. I mean ever. We've really only been doing antiderivatives.
Is it 0?
It is 0. Yeah, thank you for whoever said that. It is 0 because the derivative of x cubed is 2x squared, 3x squared, and then when you plug in x equals 0, you get 0. So here, the derivative is 0. All right. What about the inverse? I do the reflection thing. It looks like this. Of course, when I say the derivative is 0, that means the tangent line is really straight up horizontal on this side of the, at this point, right? When I do the inverse, this is the cube root of x. This tangent line now is vertical, okay? So what would that correspond to as far as the slope is concerned? Actually, a vertical line does not have a slope, or you could say it's like an infinite slope or something like that. It doesn't have a rise over run because there's no run right there. So actually, in this case, f inverse does not have a derivative at 0. It's because the slope or the tangent line becomes vertical. A horizontal tangent line has slope 0, no problem. But a vertical tangent line has no slope, or you might say it has an infinite slope. But in any case, there is no value for the derivative at that point. So this is an example where we start with a function which does have a derivative at this point, but when you go to the inverse, it does not have a derivative at this point. This is a perfectly fine function. It's okay for a function to have an infinite slope. It's just it means that it's not differentiable right there. All right. So the issue comes when the derivative is 0. So the true theorem that I'm going to write about differentiability is, move it down, if f of x is differentiable and 1 to 1, it has to be 1 to 1 in order for the inverse to be a function, then f inverse, this is going to look a little weird when I write it, f inverse prime, the derivative of the inverse. F inverse prime of x exists, that is, the derivative exists, whenever f prime of x does not equal 0. All right? There is a problem if f prime of x equals 0. It makes the derivative of the inverse not exist. But if f prime of x is not 0, then the inverse of the derivative exists. All right? And, in fact, there's a formula for the derivative of the inverse. Check it out. I'm going to write the formula, and then we'll talk about why this formula is true. The derivative, so f inverse prime, that is the derivative of f inverse of x, is this. 1 over f prime of f inverse of x. This is a weird but true formula. This is how you find the derivative of the inverse of something. This is a formula for the derivative of the inverse. And you will notice that there is going to be issues when the when you have a 0 in this denominator. That's the problem that I mentioned before. The inverse exists whenever this f prime of something is not allowed to be 0. All right. Okay, why is this true? Let's try and prove the formula. We got 10 minutes left. That's plenty of time. Proof of the formula part. It occurs to me this I didn't quite write this correctly. Can I make a little? It's not when f prime of x is non-zero. It's f prime of the inverse. Sorry about this. Can I just do this? F prime of f inverse of x is not 0. All right. Like on this picture here. You still see this picture? It's this one where the derivative, like this is your x value for the inverse. The point is that the derivative over here is not allowed to be 0. So this is the, in the language of this theorem, this is the x point, and I'm saying this derivative won't exist when this one back here is 0. It's not a big deal. Really, what I want to focus on this formula is the thing that we're going to make use of more often. All right, how you get the formula is you can prove this by doing some cute tricks with the derivative. So I'm going to start with this basic fact about inverses. F inverse of f of x equals x. This is a true fact about inverses. And we're going to take the derivative on both sides. Take the derivative on both sides. What you get? Can somebody tell me the right-hand side? What do you get when you take the derivative on the right-hand side? This is the easier side. 1. Yes, thank you. You got 1 on the right-hand side. I'm taking the derivative on both sides of that formula. Derivative of x is 1, so no problem there. On the left-hand side, this is a little tricky. You have to use the chain rule because I have something on the outside and something on the inside, right? The outer function is f inverse. The inner function is f of x. So using the chain rule, I take the derivative of the outside function, leaving the same thing on the inside function, and then times the derivative of the inside function. So what I did on the left there is the chain rule. And it looks a little weird as usual because I did the derivative of the inverse, but that's what it's going to be. Remember, the chain rule is the derivative of the thing on the outside with the same thing plugged on the inside times the derivative of the inside, like that. All right. What's next is pretty much, I'm going to write, yeah, let's write x as f inverse of y. It will be more convenient to write this around in terms of y instead of x. So then this becomes, it now says f inverse prime of, that means that f of x equals y, right? If x equals f inverse of y, then f of x equals y. That's what the inverse means. And so when I rewrite this, it says f of x here, that's y, times f prime of x equals 1. Sorry, I wanted, instead of this x here, I wanted to put f inverse y. F prime of f inverse of y, because that's what x is.
Camera's frozen.
Oh, right at the end, just when it was getting good. Thank you for shouting out. I got too excited. Okay, we're just doing some funny business with the names of the variables here, right? Instead of x, I am writing it as f inverse of y. So this x turned into f inverse of y here, and this f of x turned into y here. But now we can just solve by dividing this part. This part I'm going to divide onto the other side. So it says f inverse prime of y equals 1 over f prime f inverse of y. Right, just divided that. And this actually, this is the formula that I was supposed to be proving. I don't know if can it all fit on the screen at the same time? Almost. You will see the only difference is the variable name has changed, but that doesn't matter, right? You can write this using whatever variable you want. So I'll just write it again for emphasis in terms of x, right? If that formula is true, then it's going to be true no matter what you call the variable. And this is what we wanted to show. So at the end of a proof, this was a little proof. You could write, you know, when you're writing proofs, sometimes people write QED at the end. That's like the signal that the proof is over. I have an old textbook, like from the 19 teens. They write this word at the end of a proof, shewn. Which I guess is some kind of old-timey way of saying I just showed what I said I was going to show. They say shewn, and I kind of like that. So I will write shewn at the end of a little derivation like this. All right. So this is a strange but true formula for the inverse, for the derivative of an inverse. All right. We're not going to use this formula all that often, but there are a few times in our future when I'm going to say, hey, you remember that formula for the derivative of the inverse? And you will say, no, I don't remember it, but we'll look back at it. So don't memorize this formula, but it will come in handy every so often. All right. That is the end of this little... Oh, no, I had one example. Actually, this is going to be real quick, so this will be a perfect way to finish our class. I hope you wrote that formula down, because we're about to use it just to do this example. So, as an example, how about, here's a function, f of x equals 2x plus cosine x. And your job is to find f inverse prime of 1 using the formula. All right. You should be a little concerned when you see cosine, because cosine does not have an inverse. Cosine is not 1-to-1, but it turns out 2x plus cosine of x is 1-to-1. If you graph this, it looks sort of like, it looks like the line y equals 2x, but it's kind of wiggly. And the reason it's wiggly is because you added the cosine onto it. But the wiggliness is not enough to make it not 1-to-1. So 2x plus cosine x. And your job is to find the derivative of f inverse, even though we don't know what the f inverse is. And it would be impossible to find f inverse as a formula in this example. But you can still use that formula to find the derivative of the inverse. So what's it going to be? Well, let me just write the formula again. F inverse prime of 1 according to the formula that we just talked about, it should equal f prime of f inverse of 1, right? That was the inverse formula that we just shuned. Let's see if we can plug the business in here. So we need to know what is, I'm just trying to plug into everything that I see on the right-hand side. What is f inverse of 1, right? We should try to plug in, you know, the inside of the parentheses first. So we have to write f inverse of 1. Now, we don't know what f inverse is in this example, although in this particular problem, we can guess what f inverse of 1 is. So f of x is this function, right? Y equals 2x plus cosine x. So for f inverse of 1, we need to know some x which makes y equal to 1. So that is to say, I want 2x plus cosine x to equal 1. In this particular example, you can do this, our book says, you can do this by inspection. It means you just sort of look at it and guess the answer. Can anybody guess the answer? Some x value which makes this function equal 1? Two x plus cosine x. You might try, you know, the cosine is the weird part. You might try your favorite numbers to plug into cosine.
0.
Yeah, it's 0. 0 is my favorite number to plug into cosine. Cosine of 0 equals 1. And if you use x equals 0 here, so we can guess that x equals 0 works, right? Because it really does. 2 times 0 plus cosine of 0 equals 1, all right? In a typical example, this is the hard step. It happens to be easy just because the natural guess, which is x equals 0, actually works here. You could get lucky. Anyway, so that means f inverse of 1 is 0. So plugging in, it means f inverse prime of 1 equals 1 over, I'm plugging into this thing, right? But f inverse of 1 is 0. So now it just says 1 over f prime of 0. Can we do that? Can we find f prime of 0? I think we can. Like the f is just this function right here, and you can find f prime of 0 for this example. This is not a complicated function to find f prime of 0. So, sorry, I'm a little bit over. It's all right. What is f prime of 0? First you do f prime of x. You get 2 minus sine x, right? That's the derivative of 2x plus cosine x. And then we plug in 0. So f prime of 0 is 2 minus sine of 0. Sine of 0 is 0, so this is just 2. And so my final answer, you know, that goes right there, right? So in conclusion, f inverse prime of 1 equals 1/2. There you go. This is using that weird formula to find the derivative of the inverse. And I think that'll do it. Sorry I went over by a minute. Any brief questions? No. All right. Check out, you will see a new homework assignment posted sometime today. And it's due, as usual, on Wednesday. All right.
Awesome,
have a good weekend.
Have a good weekend.
Bye-bye.